Okay, it's 8:30, so let's go ahead and get started today. All right, good morning, everybody. How's everybody doing this morning?
Doing all right.
I'm good, hanging in there. I know it's getting really busy. It's that time during the semester. It's strange because I feel like when we're on campus, you can really feel kind of the buzz and kind of the stress levels when during this time. But we're all in our homes, so it's a little bit different. But definitely this is the time when things pick up. Okay. And so today we're going to start something new. So we're going to start a topic called fluid kinematics. Just to kind of reiterate, for those of you just kind of logging in just now, that what we cover today and what we cover on next Monday, these are not going to be on the midterm. And so the last thing that's going to be on the midterm is just the Bernoulli equation, which we finished up just the previous lecture. So, the stuff that we do today is kind of setting us up for, later parts in the class, but you don't have to worry about this for at least for this midterm. But you should still pay attention. I mean, this stuff is still extremely important, but at least, for your studying, you don't have to worry about anything that we cover today, okay? Okay, and so I think on Monday we talked about, a lot about the midterm. So I've already posted the study guide, so you can find the study guide on the Canvas site. So I posted it onto the weekly organizer for this week. So if you click on week 5, you should see the link to the study guide. So that's already up there for you guys. And I'm also going to do a pre-recorded review session. So, so normally what I like to do for these review sessions, just to make sure that it's most useful for everyone, I like to poll the class and see what topics that you would like to see the most. So on Canvas, usually every week we do a minute paper. So if you go to the Canvas site and you go to the quizzes tab, that's where the stuff is. But instead of a minute paper this week, I've put a poll up there for which topics that you would like to see for the midterm review. And so if you want to do that just really quickly, so I've basically listed out all the topics that we've covered that are going to be on the midterm. And so whichever the ones that you feel most comfortable with, just go ahead and mark those. And I plan on recording the review session this afternoon when I have some free time. So if you can fill out that survey before this afternoon, then that would be great. Then I can tailor the review session based on what people say. So just a word of advice: when you go fill out the survey, don't mark everything down, because if you mark everything down, then everything kind of goes up. So I need to see relatively which topics are giving people some more trouble. So if you mark everything, that's actually kind of the same thing as if you didn't vote at all. So try to limit your choices to just 1, 2, or 3 of the topics, and then that can really help me hone in on the review session and make it useful for everyone. Okay, so any questions on that, or just any questions about the exam, or what we covered last time that I can answer before we get started? Okay, so let's go ahead and get rolling. Okay, so the topic this week is fluid kinematics. So when you compare fluids to maybe some of your other solid mechanics classes or your physics classes, it seems kind of strange to be covering kinematics this late in the game. So we're already a third of the way through the semester, because what kinematics are basically, it's kind of the broad term for how to describe motion. Okay, and so that's basically what we're going to cover this week is how do we actually describe fluid motion. So that that definition might seem even stranger at this point of the game, because we've been studying fluids for almost 5 weeks now, and so it seems kind of strange that I'm coming out and saying that we don't know how to describe fluid motion yet. So when I say describe, I don't really mean just the words to describe it, because I feel like we have that down at this point. But in order for us to kind of move forward with some of the more advanced topics in fluids, we need some more mathematical tools and mathematical ways to describe fluid motion. So when I say describe, what I mean is just kind of mathematical. Okay. And so this will basically allow us to expand on what we covered in the Bernoulli equation and let us really delve into more topics. Because, as we saw from last week, Bernoulli is a really powerful tool to analyze fluid dynamics, but it's extremely limiting, right? So remember, we had our four conditions in which we need to apply, that need to be satisfied in order to apply Bernoulli. So it needs to be steady, It needs to be incompressible. It needs to be inviscid, which means no viscosity, and it needs to be applied along a streamline. So while there are a lot of cases that do follow those four conditions, there are even more cases that don't satisfy those conditions. So in order to analyze those things, we need some more equations. We need some more tools. Before we can actually cover those things, we need to know the kinematics. We need to know the language a little bit. Okay. And so, another way that I really like to think about kinematics is that it's really just, learning how to speak the language. And, even before that, I'd say it's, learning the vocabulary for the language. So, I'll say that, what we cover today, what we cover next Monday for kinematics, a lot of it's going to seem really dry just because it's a lot of just abstract math stuff. But then what you'll see in the weeks, after this, we're going to keep coming back to this unit because, we're going to use a lot of the descriptions, a lot of the ways that we describe fluid flow and put that in context for like viscous flow, for like control volume analysis. So, this unit itself, and this is kind of the reason why I have this be kind of the first topic after the first midterm, is that it's really just kind of a setup unit. So it's, there's not really a lot of practical situations we can apply for this stuff because it's really just setting the groundwork for, for taking off from here. Okay, and so let's start with kind of the first basic thing, which is, different viewpoints on how to describe fluid flow. Okay? And so there are two main ways that we can describe fluid flow. I'd say you can kind of think of these as kind of schools of thought. And they're called the Lagrangian. That's the first way. And the other kind of school of thought on how to describe fluid flow is called Eulerian. So that's spelled E-U-L-A-R-I-N. Okay. And so what we're going to do now is we're going to basically describe how these two kind of viewpoints view fluid particles. So let's start with Lagrangian. Okay. Okay. So people who believe in kind of the Lagrangian description of fluid flow basically view a fluid as a collection of individual particles. Okay. And so the emphasis here is on individual particles, right? Okay. And so when we apply analysis or when we perform calculations, we do this based on each of the particles. When each of these particles can move and they have its own properties and kind of move independently from each other as a function of time. Okay. And so one way that you can think about this is that the Lagrangian description will take fluid particles and tag them and then follow them throughout the flow. Okay. And so if you think of think of just a general fluid flow where we have water flowing in a stream or a river, right? And so the way that the Lagrangian description would describe this would be like this river or this stream is comprised of, all these little fluid particles. Okay? So you can either think of these as molecules or little parcels of fluid. It's the exact size of the particle doesn't really matter, but it's more of just, we take each individual particle and we kind of track it individually. Okay? And so, a Lagrangian description might look something like this, where you start with a collection of fluid particles here, and then you just follow their path, just like this. And so a Lagrangian description would say, hey, we want to look at this particle right here, right? And then the way that we're going to analyze this fluid flow is we're going to track this one particle and see where it goes, how it moves, how fast it's going, all throughout the flow. Okay? And then same thing would be for, you know, one like this. Okay, so then this particle right here would be unique and would go throughout the flow. And then we track this guy as well. Okay. Okay. And I'll draw one more and do this guy. Okay. Right. So a Lagrangian description, you know, it's you know, it follows the individual particles. So as you can imagine, you know, sometimes while this, you know, intuitively this kind of makes sense if you think of it in terms of like typical solid mechanics, right? And so Lagrangian, you know, it's this is typically the viewpoint for like, you know, like if you're doing just like traditional physics where like you throw a ball, right? So if you throw a ball across a field, you know, the way that you track that ball's motion is you follow that ball throughout there. So the Lagrangian description of fluid flow kind of came based on that. So people just wanted to apply the same kind of methods and the same kind of theory that they use for traditional physics, and they wanted to apply that in fluid. So that's kind of how this this viewpoint kind of came to be. And so this is kind of different from the Eulerian description, which actually is more common. Before I actually get into Eulerian, are there any questions on the Lagrangian viewpoint? All right, question. So would the particles travel along the path but separate from each other or stay relatively close? It could be any either one of that. So it really depends on the nature of the flow. But the idea with the Lagrangian description is that you take a particle, you tag it, and then you just kind of follow it along just like that. And so everything is just a collection of particles, as if you threw like a ball or something into the fluid and you just follow the ball throughout like that. So you can throw like a bunch of like, you know, little beads, and then you would just observe how the beads move, and that would be the Lagrangian description. So I think by itself it might not make that much sense, but when you compare it to how the Eulerian description is, it might make a little bit more sense on why these guys are different. Okay, so then let's move on to the Eulerian description. And so, you know, these, again, you know, these things are not named helpfully, so they're named after the people that created them. But, you know, again, you know, unless you actually know the definition, you have no idea what Eulerian actually means. Okay? And so what's different about the Eulerian description is that it uses this concept of a field in order to describe fluid properties. Okay? Okay? And so I think the best analogy that I can come up with is that with the Eulerian description, you're not following individual particles as they move in the fluid flow. What you're doing instead is you're kind of putting a bunch of stationary probes into the fluid, and then you're going to observe the fluids as they move past these probes. Okay? Okay. And so let's draw kind of the same situation. So let's say that we have a fluid that's flowing into a space like this. Okay? And so where the Lagrangian description, you know, we would put, you would follow each of the individual particles. Instead, for the Eulerian description, they say like, okay, we want to observe this fluid flow. But instead of tracking the individual particles, what we're going to do instead was we're just going to put a bunch of little probes into the flow like this. Okay? And so these probes don't move. They're just kind of sticks in the ground. And then we're going to observe the fluid as they move past these probes. So this probe can say something like, the fluid just moved past me at a certain angle, at a certain speed. Okay, and then that's how we end up describing the fluid flow. So instead of following individual particles and saying as a function of time, where's that fluid going, we can see here as a function of space, how does the velocity, how does the density, how does the viscosity, how does the pressure, how does that vary as a function of space. So they're different. So the Lagrangian would follow a fluid as it goes, while Eulerian just says like we're going to set up in a fixed region of space, and we're going to see how the fluid behaves in this region of space. Okay. All right. Any questions on this? Okay. And so I'll use one more analogy, because I think for these kind of concepts, more analogies are nice. And so let's think of an example where you're a biologist, and you're studying how birds migrate in the season. Okay. Okay. And so there's kind of two different approaches on which you can use to study bird migration. So you can take the Lagrangian approach. Okay. And so in the Lagrangian approach, what you would do is you would capture a set amount of birds, maybe 20 or 30 birds, and then you would place a tracking device on the birds, and then you would see where are the birds going as a function of time. Okay. So that would be, one way that you can track bird migration is you just capture just a few select birds. Usually a flock is way too big for you to track all of them, but you can at least track, a good decent number of them, and then you can get your idea from the whole migration just from that. If you want to do the study using the Eulerian point of view, what you would do is you would just set up, you would send your team out, say like, you sit here, you sit here, you sit here, and then just have them count how many birds and what direction they're going as they fly past. Okay. Okay. And so that's just kind of another way to kind of visualize the differences between, okay? And so, when we have these two methods, you can ask, which one is better? So neither of them is better than each other. They both give you important information on, for fluids and for the bird migration. But there is a method that's more common. And so the method that's more common for fluid mechanics is actually the Eulerian description. And so I think, this is kind of part of the reason why, fluids it tends to be a really difficult class, because the way that we describe fluid flow, I think, is very different than the way that we describe like solid motion. Because in solid motion is very much a Lagrangian thing. So you have an object and you track its motion, all throughout, its movement. But for fluids, in reality, it's really hard to take in a Lagrangian viewpoint, because in reality, you can't take a flowing fluid, you capture one particle and then put a tracking device on it and track it throughout, right? Even with a lot of really sophisticated experimental setups, this is something that's typically a little bit hard to do. And so the way that's a lot of fluid analysis typically goes is with Eulerian, where we look at just a fixed region of space and we see how the fluid behaves in that fixed region of space. And so, both are valid, and actually, both have their place in kind of like fluids research and fluid, descriptions. But the one that tends to be more common, especially in this class, is the Eulerian viewpoint. Okay. Any questions on this? Okay. Okay, so let's cover the next concept of the velocity field. Okay. So I think, we're all familiar with the concept of velocity at this point. And so what is the velocity field? Okay. And so, going back to our definition of Eulerian, we know that the Eulerian viewpoint, it describes fluid in terms of a field. Okay. And so what a field basically is, in mathematical terms, a field is basically just a quantity that varies in space and time. Okay. And so you can apply the field concept to any fluid property. So you can apply it to like the pressure, you can apply it to the density, you can apply it to the viscosity. So, any property that a fluid might have, it can vary in space and time. But the one that's probably the most important, and the one, that we're gonna come back to a lot, is the velocity field. Okay? And so what the velocity field shows, the velocity field is a map of how fast a fluid is moving and in what direction the fluid is moving. Okay. And so the way that we usually describe it is as a vector function. So I think everyone's kind of familiar with a vector. So a vector, you can kind of think of it as, like an X, Y, Z, in three-dimensional coordinates. It has three components. And so the velocity field also has three components, but each of those three components can be a function of space and time. And so mathematically, it looks something like this. So usually we give it the symbol V. Actually, we'll give it the symbol U. U with the arrow over it, okay? Just to stay consistent with Bernoulli. Okay? And so it looks something like this. So we have the X component. Okay? And so the X component of velocity, we actually give it the symbol U without the arrow over the head. Okay? And then we have the Y component of velocity, which we give it the symbol V. Okay? And then we have the Z component, which we give the symbol W. And this is again a function of X, Y, Z, and T. Okay? And so this right here is the X component. This is the Y component. Okay. And this right here is the Z component. Okay. And so because it's a vector, we can find the magnitude of the velocity. Okay. And so usually we give that the symbol, we give the little magnitude symbol around it. And it's simply just the square root of each of the components squared. And so we have U squared plus V squared plus W squared. Okay. And so this is magnitude. Okay. And so if you want to ask, what's the raw speed of the velocity? Speed is a scalar quantity that you get from just taking the magnitude of the velocity field. Okay. All right. Any questions on? Oh, go ahead.
Is W not squared in that magnitude?
Yes, W is squared. I just drew it weirdly because it's at the bottom. There you go. All right, any questions on this?
Professor, does Bernoulli's equation respect Lagrangian or Euler's?
Yeah, so Bernoulli's is actually more of an Eulerian thing because when we did Bernoulli's, we talked about the velocity at this part, right? So remember we did like a nozzle, and so we talked about the velocity at the left side of the nozzle and the velocity at the right side of the nozzle, right? And so just by having two velocities at two different locations like that, that's kind of a naturally an Eulerian way to describe it. Yeah.
Okay, thank you.
Yeah, Lagrangian actually, actually we hardly ever see it at all in this class. Actually, I don't know if we ever see it at all, but Lagrangian is kind of used more for kind of very advanced like fluid experiments types of things. But for kind of introduction to fluids, it's almost all Eulerian. Okay, so let's do an example just to kind of illustrate this. So this is just to kind of give you an idea of what a velocity field is and how to visualize it. And so in this example, we want to sketch velocity field. And so this is only a 2D velocity field. And then it's going to be given by the following. So we have u is equal to minus x. Okay, and then v is equal to y. Okay, and so if you put this into vector form, it would look like this. So the vector is equal to minus x, y. Okay. Okay, and so right away you'll see that this is a steady field because there's no time dependence. Okay, and it's also 2D because we only have two components. Okay, and so let's plot this field. And so the way that we're going to plot this field is that we're going to basically, just like in the Eulerian viewpoint, we're going to do this at kind of fixed locations here. Okay. And then at each location, what we're going to do is we're going to draw a vector according to the components of what this guy right here. Okay. Okay, so let's start at the origin. So the origin, we have origin has the coordinates 0, 0, and so when we plug in 0 into here and then 0 into here, all we get is just 0, right? And so we have no vector here at the origin. Okay. All right. So next, let's plug in the components for this vector or this location right here. And so the components for this is x equal to 1 and y is equal to 0. Okay. And so we plug those in, we get a vector of negative 1, 0. Okay. And so negative 1, 0 looks like this. Okay. So it's just a vector pointing to the left. Okay. And so if we continue that trend along, we basically get a bunch of vectors that point to the left, just like that. Okay. And of course, they should be growing in size because we have x right there. So as when we plug in 2, we get negative 2, 0. When we plug in 3, we get negative 3, 0. Right. So all of these should be growing in size, but I only have so much iPad here. Okay. Okay. So now let's plug in values on the y-axis. So if we start plugging in values of y, so we plug in this point right here, which has the coordinates 0, 1, and so 0, 1 we have a vector of 0, 1 like that, and so that's going to be an up arrow, up arrow, up arrow. Okay. And then similarly for below the y-axis, so we're going to have down arrows like that. Okay. Right. And then to find out all the other locations here, all you got to do is plug in the coordinates into this formula right here. Okay? And so let's plug in 1, 1. Okay? And so the velocity at 1, 1, we'll just plug that in here. And so for this velocity field, we have -1, 1. And so this is our velocity. Okay? And so a vector of -1, 1 looks like this. Okay? And so I'm going to go ahead and fill in kind of all the rest here. And of course, this is not exact. You know, these are just kind of approximations. Okay. And so, you know, the way that you plot a velocity field is that you take the function and you just plug in, you know, the x, y coordinates of that, and you get a vector. And then at those locations, you point the vector in the direction of the velocity. Okay? And so if we actually wanted to visualize the velocity field from here, you know, the velocity field is basically just going to follow these arrows. So it would go kind of like this. Okay? Okay. And so this velocity field right here basically models the same, you know, if you took a hose and you hose down your wall, and that's kind of shows how the velocity splits. Yeah, so there's a comment to the chat. So this reminds me of the slope from fields from calculus 1. That's exactly what this is. So it's exactly just a slope field from calculus 1. Yep. Yep. So to get a velocity field, you just draw out the arrows at every location, and then you can draw, you know, streamlines that kind of go through all those guys.
I have a question. For
Sure.
the x direction, is it always negative, or is it only negative because it's stated that the velocity is going in the negative direction?
Right. So it's only negative here just because that's this example. But in reality, you know, you can have, you know, positive, you can have quadratics, you can have all kinds of crazy things for the velocity. But yeah.
Okay.
All right. Any more questions on this example? I'll say that this is much nicer on the iPad with the colors. So, you know, in the past, I've done this on the board with just all black, and it sucks. So this is much nicer with the colors. Okay. Okay. So I'll just make one comment. So we've already kind of talked about this in Bernoulli, but I think it's worth talking about again. And so the field that we just saw previously was a steady flow. And so we can give steady kind of a more precise definition here. And so when we say steady, a flow is steady, what we mean is the velocities are not changing. Okay. And so in mathematical terms, it looks like this, basically. And so if we take the partial derivative, don't be scared of the partial derivative. We're not actually going to compute it. But the reason I do a partial derivative here is because, remember, the velocity depends on space and time. And so if we're just taking the derivative with respect to one of those variables, it's just going to be a partial derivative. But when I say steady, all it means is that if you take the derivative of the velocity with respect to time, then it's just going to be 0 because nothing is changing with time. And so the way that we you know, describe a steady flow in words is say, you know, the velocity is not changing, and mathematically all we do is we just take the derivative with respect to time and we say that it's 0. Okay. And so you can put this another way is that you can say that the flow is not accelerating or decelerating with respect to time. And so if you have unsteady flow, you know, obviously this is going to violate this. But for most of the things that we'll cover in this class, we're going to do steady flow, just because when things start to get unsteady, then it gets pretty crazy. And actually, in reality, you know, most of the time you'll have to use some kind of a computation of fluid dynamics or some kind of computer program for unsteady flow. There's some analytical methods for unsteady flow, but it's extremely limiting. So So for just simplicity, we're going to assume most of the flows are going to be steady. But just know that unsteady flows are out there, but most of the time you need a computer program to analyze them. Okay. So that's the velocity field. So, the velocity field is usually something that's really important for fluids because it really, it describes where the fluid's going and what direction. Okay. And so the next thing that we'll cover is kind of one step up from the velocity field, which is the acceleration field. Okay. And in particular, we're going to go over one a very important mathematical construct for fluids, which is this idea of the material derivative. Okay. Okay. And so, we're all kind of familiar with the concept of the derivative at this point, where the derivative, just like, the slopes that you saw in calculus, a derivative expresses a rate of change, right? Okay. And so, for a lot of the functions that you've probably seen in calculus, you would take, dy dx. And so what dy dx expresses is how does the function y change with respect to the function x. Okay. And so for fluids, things are quite complicated because a lot of things can change in fluids, and then they can change with respect to a lot of different things. Okay. And so for fluids, especially in the Eulerian viewpoint, things can change in a fluid with respect to time and with respect to space. Okay. And so because we have this, very complex, form of, or, ways that things can change, we need to kind of expand our definition of the derivative in order to account for all these different changes. Okay. All right. Any questions on this? Okay. Okay. So let's talk about, each of the different ways they can change and kind of give some kind of physical motivation behind it. Okay. So let's first talk about time. And so when I say that things in a fluid can change with time, what I mean is that if you kind of sit in a fixed location in the flow and you observe things changing around you, then that's something that's just purely changing with time. Okay. And so one example that I like to think about this is that say that you're you're a little pixie like Tinkerbell or something, and you can sit at like the edge of a garden hose. Okay. And so when you're sitting on the garden hose, when it's off, you don't see any flow at all. But say that, you don't move at all, and then someone turns on the garden hose. And so just by sitting at that place and just by someone turning on the garden hose, you observe the fluid go from nothing to something that's really fast, and you didn't have to move at all. Okay. And so just by time, just by you know, not even moving, you know, things in a fluid can change. Okay. And so now let's talk about space. Okay. And so in addition to time, you know, you can observe changes in the fluid just by moving from one location to another. Okay. And so taking our same example of a garden hose, now let's say that, you know, you're in the garden hose, but you're following the flow. And so you're moving from one location to the other. Okay. And so, you know, every garden hose has a nozzle at the end, right? Okay. And so the flow is coming this way, right? Okay. And so coming into the nozzle, you know, we have a velocity coming in, so we'll call that V1. And we also have a velocity coming out, which is V2, okay? And so we saw, you know, we just saw this on Monday. So just because of conservation of mass, we know that V2 is going to be greater than V1, right? Just based on the fact that the outlet area of V2 or at V2 is less than the outlet area or the inlet area at A1. Okay? And so if you're like a little you know, pixie, you're following the flow, and you go from this location to this location, so you move from here to here, okay? So what you observe in that case is a change in velocity, and all you did was change your location. So that's what I mean by changes in space, okay? And so if you move to different locations in the fluid flow, you know, you're going to see different velocities, you're going to see different, you know, densities sometimes, different pressures, different viscosities. So just by changing your location, you can observe changes in fluid properties, and that's a change in space. Okay. Okay. All right, any questions on this? Okay. Okay. And so now let's put this in mathematical terms. So let's kind of remind ourselves that our velocity is a function of space and time. And so just for the sake of oh, okay, so it looks something like this. So again, remember, it's a vector function that depends on space and time, just like that. Okay. Okay. And so we can say that the velocity depends on x, y, and z, but x, y, and z themselves are also functions of time. Okay. And then the velocity itself also depends on time. Okay. And so we want to compute the acceleration. Okay. And so to compute the acceleration, we know that we just take the derivative of the velocity with respect to time. Okay. Okay. And so if you remember from multivariate calculus, if we want to take the derivative of a function where its independent variables itself depend on, you know, something, then we have to use a very special rule called the chain rule. Okay. And so you might not have seen chain rule like this, so I'm going to kind of break it down. But first, let me write out all the different terms. So first we have this. Okay. And so because the velocity itself depends on time, right? And so we can just take the velocity and take a partial derivative with respect to time. Okay. Okay. Next, due to chain rule, we have this this term right here, and so we're going to have the derivative of the velocity with respect to x, okay? Because the velocity depends on x. But then because of the chain rule, we have to take the derivative of x with respect to time. Okay. And so next we have the y term. So this is going to be derivative of velocity with respect to y, derivative of y with respect to time. Okay. And then finally we have the z term. And so the z term is going to be dv, dz, dz, dt. Okay. And so by taking the derivative of time of a velocity, we have 4 terms that come out because we have our velocity depends on 4 different variables. Okay? And so all these just came out just from the chain. Okay. 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 And so now that we have this chain rule, I want to draw your attention to all of these guys right here. So we have the derivative of x with respect to time, the derivative of y with respect to time, and the derivative of z with respect to time. Okay. And so x, y, z here, they represent nothing more than just the positions of certain places in the fluid. Okay. And we know that when we take the derivative of position, we get velocities. Okay. So all these guys actually we can replace with the velocity components. Okay. And so if we do that, we end up with our material derivative. Okay. And so our material derivative, it has 4 different terms. So first we have the first term with respect to time. Okay. Next we have this next term. And so dx dt, remember we're gonna replace that with the x component of velocity, which is u. Okay. Okay. And that's gonna be multiplied by dv dx. Next we have the y term, so that's gonna be v times dv dy. Okay. And so notice the difference between the v with the arrow on top, which is the velocity vector, and then v with no arrow, and that's just going to be the y component of velocity. Okay. And then finally, we have the z term, which is w dv dz. Okay. And so this right here is our material derivative. So I know it looks scary because it has a lot of partial derivatives and a lot of terms that we don't know. But just rest assured that we're never actually going to compute this. It's more just kind of a mathematical tool for us to kind of understand how things change in a fluid. And so what we're going to do next is I'm going to take each of the mathematical terms here and describe to you what they represent. And that's going to be the extent of what you need to know. So don't worry, you're never going to actually compute this. It's just for kind of conceptual understanding of how things vary in a fluid. If you want to pursue fluids at a graduate level, this is something that we're going to work with more over there. But for now, it's just enough just to kind of understand what each of the terms represent and what their physical intuition is. Okay. All right. Any questions on this? Okay. Okay. So let's categorize the different terms in the material derivative. And so the first term that we'll go over is the unsteady term. Okay. And so the unsteady term is just the partial derivative with respect to time. So it's the first term in our material derivative. So that's partial v, partial t. Okay. And so remember before this, when we went over our analogy with the garden hose, this represents changes with respect to time. And so another way that we can call this is, because this is a change at a fixed location with respect to time. Oh, I forgot time. Okay. Another way that this is called the local rate of change. Okay. Local meaning that it's it's only at a small fixed location. Okay. And so now let's go over, that's kind of the first group of terms. So I call it a group, but it's just one term. Okay. And so all the other terms in the material derivative, they make up the second group, and we call these the convective terms. Okay. And so the convective terms are the u partial v partial x plus v partial y plus w partial v partial z. Okay. And so these are going to match up with the the changes with respect to space that we talked about in our garden hose. Okay. Okay. Another way that we can describe this is because we have the product of the fluid velocity and a spatial derivative. These are changes that occur as you flow with the fluid. Okay. Right. So those are kind of the two groups of terms of the material derivative. So one of them is just the unsteady term, which describes just changes in time, and the other one is the convective terms, and those represent changes in space. Okay. All right. Any questions on these? All right, so we've motivated this idea of the material derivative by taking the derivative of velocity, but you can actually apply the material derivative for any other fluid quantity. And we'll actually see that, as we go on from here. So we're going to apply it to the mass of the fluid or the density. We're going to apply it for the momentum of the fluid, and we're even going to apply it for energy too. Okay. And so the general term for the material derivative looks something like this. Okay. And so actually, the kind of the traditional symbol for the material derivative is we use capital D. Okay. And I'll leave parentheses here for just whatever quantity that you want to apply. Okay. And so it just looks just like this. Okay. Right. And so, everywhere we basically just took our material derivative, and everywhere I had the velocity vector, I just replaced it with something generic. Okay. And so one thing that you'll you know, if you're taking heat transfer in the spring, what you'll see is that, you know, they apply this material derivative for temperature, actually. So if you want to, you know, see how the temperature in a fluid changes, you know, in time and space, you just plug in big T in here. And so you have big D, big T, okay. dt is equal to partial T plus U partial T partial X plus V partial T partial Y, okay, plus W partial T partial Z, okay? Okay. And so that's the material derivative of temperature, okay? All right. And just you know, if you're curious, you know, sometimes you know, what you'll see, you know, the more you work with them, the more you see, is that mathematicians are incredibly lazy people, and so, you know, for a lot of them, writing out all these partial derivatives is too much work for them. So if you're curious to see kind of the shorthand notation for this, it looks like this. Although if you don't know what these symbols mean, then this is not that helpful, but you know. Just in case you see it in this form elsewhere, this is basically the same thing. Okay. And so this down here is another form of the material derivative where they replace that the convection terms. So they replace these guys with this symbol right here. Okay. And so you can see they replace it with the velocity vector with the arrow overhead, dot product with nabla. And so if you've never seen nabla before, nabla is just a vector with all the partial derivatives. Okay, and then you have your quantity over there. So, you know, not something we're going to use in this class that much, but in case you were curious, you know, that's kind of the they call this kind of the vector form notation of the material derivative. Okay. All right, any questions on this? Okay. Okay, so the last concept that I want to go over today is the difference between systems and control volumes. Okay. And so, you know, I'll preface this by saying that, you know, this difference between systems and control volumes, these connect very closely to the differences between Lagrangian and Eulerian, which we covered at the beginning of class today. So kind of put that in kind of your mind right now, and it should help to kind of frame this guy, okay? Okay, and so just to kind of give you a preview of where we're going in the next couple of weeks, what we want to do is we want to express kind of our very basic conservation laws, and we want to express them for fluids. So, you know, we have things like conservation of mass, conservation of momentum, conservation of energy, conservation of angular momentum. We'll even touch on that a little bit too. Okay? And so, you know, we have kinds of, you know, expressions for these for, you know, solid objects, but we want to express kind of the same things for fluids. But, you know, we need a lot of the mathematical tools that we covered just previously, and also what we'll do next Monday. Okay. But, you know, in order to apply these conservation laws, we need to be able to do it to a constantly moving fluid. Okay? So we want and we can do it in kind of two different ways. So we can apply conservation laws to a system, or we can apply the conservation laws to a control volume of space. Okay, and the differences are this. Okay, so let's start with a system. Okay, and so a system, just to kind of sum it up in a few words, is a fixed amount of mass. With emphasis on the mass. Okay. And so the system approach is typically what you've probably adopted for, like, you know, your strength of materials and your kind of traditional classes. Okay. Because solid objects, you know, a fixed thing of mass is very easy to follow. Okay. And so say that you have like a block of concrete. Okay. Right, so this block of concrete here is a fixed amount of mass because it's a fixed amount of concrete. Okay, and then if you want to track the motion of this concrete, say if like Hulk angry, right? Right. I tried to draw him with buff arms, but I guess he skips leg day. So Hulk takes this block of concrete and then chucks it across the room, right? If you want to analyze the motion of this block, you know, you can say that, you know, we have this fixed amount of concrete right here, and we're tracking the motion of that concrete as it gets chucked across the room. Okay. Oh yeah. So the title of this is Systems versus Control Volumes. Okay. And so this, you know, this approach to tracking just a certain amount of mass, you can think of this as kind of the same as our Lagrangian viewpoint. Because remember, for the Lagrangian viewpoint, we have individual particles, you know, that we're tracking the fluid, and each of those particles will have like a fixed amount of mass. And so a system view of like performing analysis is kind of the same thing, where we have a fixed amount of mass and we track it, right? And so for fluids, you know, this is usually pretty difficult because, like, if you take, you know, say you have water that's flowing in a river, and you say, I'm going to track this specific set of like 3 kilograms of fluid, and, you know, as it flows to the river, it's going to go like all over the place. So it's usually, you know, a little bit difficult. So, you know, the system approach works pretty well for solid mechanics because a mass typically stays together really well. But for fluids, it's not as effective because the mass kind of disperses and spatters, you know, along with the fluid flow. Okay. Okay. Any questions on this? Okay. And so what's common for fluids, and this will actually be the subject for the next, you know, 2.5, 3 weeks, is a control volume approach. Okay. And so the difference between a system and a control volume is that a control volume is a fixed region in space. Okay. And then from this fixed region in space, you know, if we say that, you know, going back to our river analogy, say that, you know, we want to analyze this region, you know, as the Mississippi River crosses, you know, this city right here, right? And so from that fixed region of space, fluid's going to flow into and out of this region of space. And then based on, you know, the observations that we can make from the fluid, we can analyze, you know, its properties. Okay. And so, you know, connecting this back to the beginning of this lecture, this is very much an Eulerian way to describe fluid. Okay. And so just to kind of illustrate the differences between systems and control volumes, let's do an example. Okay. And so let's say that we have a garden hose. Okay. I'll draw 2 of them. Okay. And then in the garden hose, what we're going to do is we're going to see, you know, how do we analyze, or how would a system analyze the fluid here, and how would a control volume analyze the fluid? Okay. And so on the left here, we'll have system. Okay. And on the right here, we'll have control volume. Okay, so let's start with the same kind of thing. So let's say for our system, we'll identify this region right here, or this this amount of mass. Okay, and so we'll say that we'll start with the mass of the fluid that's in here. Okay, and the control volume will define our region to be the exact same. Okay. Okay. And so let's see how these two evolve as the fluid flows. Okay. Okay, so remember a system will follow this fixed amount of mass. Okay, so as we turn the hose on, this fluid here is going to come out of the hose, right? And so the way that we can see that is something like this. Okay. And so because we turn the hose on, the mass is going to exit the hose. Okay. And then since we're in a system point of view, we have to follow that mass exactly. Okay? And so following that mass, what that means is that, our system is going to move outside of the hose. Okay? Okay. And so remember, a system, you can think of it as tagging a certain amount of mass of the fluid, and then just following it, as it goes. So, for the hose, this means we just, let it leave the hose, and we keep following it until it splatters onto the ground. Okay. Okay. And so for control volume, remember, control volume is nothing more than just a fixed region of space. So, for the control volume, it starts like this, and we can turn the hose on. And then even as we turn the hose on, the control volume is just going to be like, it's not going to move because it's just a fixed region in space. Okay. And so the way that we're going to analyze the fluid flow in this control volume is we're going to measure basically the amount of fluid that's coming in, and then we're going to compare that to the fluid that's coming out. Okay. And we're going to see how things like mass, like momentum, like energy, how does that change as you go from the inlet and to the outlet? Okay? And so this is kind of form the basis of the fluid analysis that we're going to do here. Okay? All right. All right. Any questions on this? Okay. So that's the differences between systems and control volumes. And so, we're going to be working mostly with control volumes, but it's also important to kind of understand what a system is, especially within the context of a fluid. So a system, is a fixed amount of mass, but because the fluid is often moving, that's something we're going to follow as it goes. Okay, so the next topic is going to form kind of the basis this is kind of the theorem that we're going to use for that we're going to apply conservation of mass momentum to, and it kind of mathematically describes exactly what I told you just now, and that's called the Reynolds transport theorem. And it's so important for fluid mechanics that it actually gets an acronym. And so, Reynolds transport theorem is often abbreviated RTT. Okay. Okay. So what Reynolds transport theorem is it gives us the framework on which we can use to apply our conservation laws. Okay. And so just some examples of the conservation laws, we'll have conservation of mass, conservation of momentum. We'll touch on angular momentum a little bit. And we'll also do conservation of energy as well. But the unfortunate thing is that applying these conservation laws for fluids it's not very convenient because the fluid is kind of always moving, so it's never kind of staying in one place. Okay, and so the way that we actually apply these is with the Reynolds transport. Okay, and so before we move on, let's kind of revisit the difference between an extensive property and an intensive property. Okay. And so the relationship between an extensive property and intensive looks like something like this. Okay. Right, so I'm just using a generic B here. So B can be anything. But for any property that you have in a fluid, there is an extensive version and intensive. Okay. And so this capital B right here, this will be our extensive property. Okay. And so some examples of like an extensive property would be like mass, momentum, kinetic energy, okay, and so this little m right here, this is actually mass, okay. Okay. And then this little b right here, this is the corresponding intensive property. Okay. And so some examples of this would be like momentum per unit mass. Okay. Or energy per unit mass. Okay. And so remember kind of the definition between these two. So, an extensive property, this depends on how much of the substance that you have, right? And so the more stuff that you have, the extensive property will grow, right? And so like if you think of like tissue paper, right? And so the more tissues that you have, the more mass that they're going to have, right? The more tissue paper that you chuck across the room, the more momentum it's going to have, right? Whereas an intensive property doesn't depend on the amount of mass. So it doesn't matter how many tissues that you have, right? You can have like 1 million tissue papers, they're still going to have the same density because density is intensive property. Okay, but you have 1 million tissues, its actual mass will be more than that. Okay. Okay, and so the idea behind the Reynolds transport theorem is that it connects the rate of change between these two guys. In a fluid. Okay. And so, even though these two things, they're obviously connected to each other, like density and mass, oftentimes we don't consider their rates of change together. So what Reynolds transport theorem will let us do is be able to connect the rates of change of an extensive property and the corresponding intensive property. Okay. All right. Any final questions on this? Okay. So that's all we got time for today. So thank you everyone for tuning in. So remember to fill out the survey on the Canvas site for what you want to see for the review session. So I plan to record the review session after lunch today. So if you get it to me, if you fill out the survey before 1:30, then your opinion will be heard for that. Okay. And then I plan on posting the review session basically right after I have it, right after I finish recording it. So you'll have basically the review session a week before the exam. That was kind of my goal. Okay? And I know I still need to upload the solutions for homework 2, so I'm going to do that basically right after this too. But your homework 2 should be graded, so I graded that on Monday. I just haven't had a chance to upload the solutions yet. So check out your grade, check out the comments that I sent you, and then look out for the graded or for the solutions coming this afternoon. Okay? So thank you everybody for tuning in. I hope everyone has a good day, and I'll see you on Monday.
Thanks, Professor.
Thanks, guys.
Our exam's on Wednesday, right?
Our exam is on Wednesday. Yes.
Yeah, that's what I thought. Okay.
Mm-hmm.
And
Sure.
homework 3 is still due on Monday.
Yeah, homework 3 is due on Monday, and so since homework 3 is going to be due kind of right before the exam, as soon as as soon as the deadline passes for homework 3, I'm going to upload the solutions for that too, so you can have that to study as well.
Okay.
Yeah. Okay. So the control volume diagram, sure. And so this is just kind of the difference between a system and a control volume. So remember, a system will follow a fixed amount of mass. Okay. And so what we have here in this diagram here is that for the system, what I said was that I'm going to take this amount of mass right here, and then I'm going to follow it kind of no matter what. So you kind of think of it as like we're kind of stalking this amount of mass. And so as soon as we turn the hose on, and then this amount of water leaves the hose, we're going to keep following it no matter what. So this fluid comes out. We follow it, and that's what it means to have a system, is you have a fixed amount of mass and you just follow it. Okay? Whereas a control volume is just a fixed region of space. And so what we can say for the control volume is that we want to find out more information about the flow in this hose, and so we're going to take this fixed region of space, but even after we turn the hose on, we're just going to sit here because the control volume is just a fixed region. So as the hose goes, the water is going to flow into the control volume and out, and then we're going to learn more about the fluid just by how the fluid comes into the control volume and comes out of it. Okay? And so that's kind of the difference between them. Yep. Mm-hmm. Yeah, last semester, someone gave a really good analogy for this, where like, say you have a daughter that's just starting to date. And so kind of the system or the Lagrangian way to kind of make sure that, nothing happens on her date would be to like take your car and just kind of follow her around everywhere. But the control volume approach would be to, sit at your house and just track her from her phone, install like Life 360 on her phone or something like that, and then observe that way. So, I thought it was really creative, but it's, I hope, we all grow up, we don't do that to our daughters.